It's day 8 of Advent of Code. Let's see how it goes today. So we have day 8 ready here. So we're gonna work with Resonant Collinearity. So we have some antennas. And each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter, or digit. So this is going to be our map. And the signal only applies to its antinodes based on the resonant frequencies of the antennas. So two antennas of the same frequency create antinodes which are perfectly in line with them. But only when one of the antennas is twice as far as the other. So it means that the antinodes appear like outside of the antennas in line, one on the one side and another on the other side, in the same distance as those antennas are. So basically we just add up the differences in both coordinates and we get the same. They show up on the sides of the line, kind of. When we add another antenna, it creates additional antinodes, but those which are outside the map are not counted. And antennas with this different frequencies don't create antinodes, so A doesn't create anything here. Okay, that makes sense. So yes, so this one, those ones, like trying to understand how those things are created. So this one is created by this one, yeah. So A, these ones create these ones. Okay, that kind of makes sense. Not sure where this one comes from. Where does this one come from? Oh, it's created by these two A's. So it creates this one. And antinodes can overlap antennas as well. Okay. And the goal of this is to calculate the unique locations of the antinodes on the map. So if two pairs of antennas create the same antinodes, it's just still one location. So in terms of description, it seems quite easy, and this is a very small input, so it should be pretty fine to go brute force and calculate all the options. So let's actually try this with the sample input first. So let's take the sample input, and what we will be doing is so we will have private width, private int height, and then we will be reading in the input. So for while wait exactly, so we read the input, we read so the line, so width will be line length, and height we will increment here, and we will be reading it into a list string lines. And I should actually create a helpful method here, something like read all lines. So let's do stream reader extensions. This can be useful for later as well, so worth doing now. So let's create that. So it's gonna be a read all lines async. So this what we'll do is we'll create a list of string lines, and then we'll read it while possible and then return, and this is gonna be a list, or we can do a list of a string as a result. So it's gonna be lines. Yes, nothing too complex here. I think it's just fine to keep it like this. So we can now use this new method. Await input reader read on lines. Nice. So we have now our lines, and now width will be the length of the first line. Height will be a number of lines. And now what we will create is the grid, exactly. We will just turn this into a grid of lines. So line, X, Y, yes, perfect. So we have the map now. And now we'll be looking for pairs of characters. And what we can do actually is when we encounter a non-dot character, so if line x equal dot, then we can store that into some kind of tracking location. So we can do a dictionary of char, and there will be a list of point and antennas. So we'll be tracking all the antennas in a dictionary of lists. So for all the different kinds of antennas, we will track all the locations where those are. So if antennas and so what is the right spelling of this one? Antenna, 2 ends, right? So antennas, try get value from, if it's, we cannot get the value of, well, let's store it in a variable. So character, let me store that character here, and then we do character, and then we do character out var point list. Now if it's not there, we create it. So find list equals point and store it, and then we just add it to the list, and we add it. So point list add XY coordinate. So now we are storing all the locations, and now that we have them, we can use that to easily calculate all the pairs. So for each type in antennas. So the antenna type is the key, but we need the points. And now for each pair of them, so we'll do for antenna Y, antenna 1, for antenna 2, it's going to be +1 minus less than points count. So we start from the next one because we don't want to create, we don't want to process the same antenna in both loops. So now we have to do antennas. So diff is going to be points antenna 1 minus points antenna 2. So we get their difference. So if it's, or rather, so it's nicer, I will do it this way. So if you imagine them located like this, so the difference will be like 2, 2. And what we need to do is to do antenna 1 minus, or, so the difference will be, oh, let's see. So if we do the second minus first, then we do first minus difference and the second plus the difference, right? Am I not mistaken? Hopefully not. Not completely sure, but so now we have some kind of hash set of point antinodes. We'll do add points antenna 1 minus diff and antinodes point antenna 2 plus diff. So this will give us the 2 points, although we have to make sure they are both in bounds. So we can do that processing afterwards, or we can do it right away. So we can do return denotes where is in bounds p count, and is in bounds. Let's do that method. So private pool is in bounds. It's going to be point p. So we just check if it's within the bounds of the map itself. So this is the right check here. So unless I misunderstood something, this could be working. So let's see what happens if we run it against the sample data. So we have day 8, 14 locations. That is okay. So let's see the big input and save it. And let's pick the input file. So here we go. 341. Okay, so the first part is done. So now let's on to the next one. So after the historians asked us if we took the effects of resonant harmonics into calculations. After updating our model, it turns out that antidote occurs in any grid position exactly in line with at least 2 antennas of the same frequency, regardless of distance. This means that some of the new antinodes will occur at the position of each antenna as well. So it seems that now the antennas create like all the multiples of frequencies. There and the antennas themselves are also antinodes. So Ryan 2, 3, 4, So it's like that. Okay, so 9 antinodes generated by these antennas. So it seems like we just need to calculate the multiples of the locations. So let's see what happens with the test input. I'll take our solution so far. Now we definitely need to check for the bounds before we actually add those locations to the list. So I will be checking that here. And we'll be doing while so current point location will be points antenna 1, while is in bounds current location, and do so we will add antinodes at current location, and then we will do minus equals diff, and then this will add the locations from the first antenna, and then on the other side then we do current locations here and do plus equals diff and just validate if it's in bounds, and like that. Is that it? Like, it seems simple enough, but maybe I'm missing something. So let's see. Test data 34, and that is correct. So let's get the puzzle input. Well, this is the same thing, right? So let's try it with the input file. 1134. And that is correct. Okay, so that's pretty good. I thought the second part will be much more complicated than this. And it was, in the end, quite easy. So, yeah, I mean, we have completed day 8 of Advent of Code 2024. So let's see how we go about day 9, and also check out my next video on how ChatGPT will fare against this problem. We'll see if it handles it or not. So thank you very much for joining. See you on day 9.